welcome back to our machine design series, where today we are going to do a brief overview of materials and materials processing in machine design. And we're going to focus pretty heavily on steel. Now you might ask why. The answer is really fairly simple. Steel is everywhere. It is one of the most commonly used materials in mechanical systems because of its strength, versatility, cost effectiveness. So whether we're talking about shafts, gears, fasteners, frames, steel is often the default choice in machine design. It's also handy because its properties can be tuned. We can change the carbon content, add alloying elements, or apply different heat treatments. And all of those processes will help steel meet a wide range of design requirements. So let's jump in to explore what steel is, how it's classified, how we can manipulate its mechanical properties, and why that matters when we're designing real-world components. We will also connect this to material behavior, hardness, and loading types, things that directly impact how and when parts will fail or survive in service. So let's start with the basics. What is steel, and why isn't pure iron good enough for standard use? Steel is an alloy made primarily of iron and carbon. In its pure form, iron is actually quite soft and not particularly useful for most engineering applications. By adding carbon, we can significantly change and improve the mechanical properties of the steel metal. When carbon content is between about 0.05 and 2% by weight, that is when we will classify the material as steel. And then cast iron is steel with more than 2% carbon by weight, and cast iron has different properties and applications than steel. Beyond just changing carbon content, we can also change steel's properties by adding other alloying elements. For example, if manganese content exceeds 1.65%, if silicon is above 0.5%, or if copper is over 0.6%, or if other elements like chromium, nickel, molybdenum, vanadium, or tungsten are present in specific minimum amounts, then the material is classified as an alloy steel. These elements can help improve material properties like strength, hardness, or corrosion resistance or toughness. Finally, heat treatment is another major way to modify the properties of steel. By carefully controlling heating and cooling cycles, we can alter the internal structure of the metal and tailor it for different applications. So whether we want it harder, tougher, or more ductile, heat treatment can help us achieve that. Okay, so let's talk through some carbon levels for different steels and their most common properties and applications. Okay, let's start off with a low carbon steel. Low carbon steel is highly ductile, it's easy to machine, easy to weld, and that makes it cost effective and commonly used for many structural applications. All right, next up we have medium carbon steel. Medium carbon steel is a balance between ductility and strength. It has moderate weldability and machinability, and it is often used in applications requiring good tensile strength and toughness. So applications like shafts, gears, axles, and pressure vessels. Next up, you guessed it, it's high carbon steel. High carbon steel is stronger but less ductile. It's typically used for tools and springs thanks to its ability to be hardened. Okay, and we have one more line in our table, and that is for ultra high carbon steel. It is extremely strong but brittle, making it ideal for specialized applications requiring extreme hardness and wear resistance, although it's costly and difficult to machine or weld. So this is used in applications like knives, chisels, and other wear-resistant components. And that completes our table. So you can see that there is this trend from low to high carbon steel. We are decreasing our ductility. The material is becoming more brittle. We are decreasing our machinability. It's becoming harder to machine. We are decreasing our ability to weld the material. But the trade-off is we are increasing our tensile strength. We are increasing our ability to harden through heat treatment, although at a higher cost. And then these last two columns just give you some common ways that the materials are formed and their most common applications. Now let's talk about how to identify these different types of steel through a numbering system. So in 1975, SAE introduced the UNS, or Unified Numbering System, for metals and alloys. Around the same time, the American Iron and Steel Institute, or AISI, adopted a very similar system, and these systems were created to bring consistency and clarity to how we classify and identify different metal grades. The UNS system includes 6 characters. The letter prefix designates the type of material. All right, so the letter prefix could be a G, which would indicate that it's a carbon and alloy steel. It could be A, which would indicate that it's an aluminum alloy. C would indicate a copper-based alloy. S would indicate stainless or corrosion-resistant steels. And then the first pair of digits, which comes after the letter, gives the composition, excluding the carbon content. And you can see section 2-8 in Shigley for a table that gives you pairs of digits along with the letter prefix and indicates the type of material. So for example, G33 being the first 3 characters of the UNS number indicates that it is a nickel chromium type steel. The second pair of digits will give the approximate carbon content. And finally, the last digit is for special situations. The SAE and or AISI numbering system is the middle 4 digits of the UNS number. Some special situations might be small variations in the composition or in the processing of the metal. So let's take a look at an example. So if you see a UNS number of a steel that is, let's say, UNS G10 180. I want you to take a look at this and tell me what the composition of this material is. And by the way, if you were to get its SAE and or AISI number, it would simply be 1018. And you're going to need the table from section 2-8 in Shigley to be able to solve this. In that table, it tells you that G10 indicates a plain carbon steel. The next two digits indicates the carbon content. So we have 1,8 for those two numbers, and that indicates that we have a 0.18% carbon content. The last digit is for special situations. It's a 0, so that indicates that we don't have a special situation here. All right, let's take a look at another example. How about AISI number 4140? Again, you're going to need that table from section 2-8, and it will tell you that G41 indicates that we have a chromium molybdenum steel alloy, and the 40 indicates that we have 0.40% carbon content. We could also go back and look in our previous table at the carbon content of these two alloys and say that this 1018 steel, it has 0.18% carbon, and so therefore it is a low carbon steel. So it's going to be highly machinable and weldable, but not easily hardened. And then if we take a look at our next material, this 4140 steel, we can see that its carbon content is 0.4, putting it into the medium carbon steel category. And so it's going to have a balance of ductility and strength. One more note is that stainless steels are sometimes just referred to by their alloy content. So S3200 is often called a 18-8 stainless steel, meaning that is 18% chromium and 8% nickel. All right, now let's talk about some manufacturing processes, hot working and cold drawing. So hot working refers to shaping a metal while it's heated above its recrystallization temperature. And at this temperature, the metal is soft enough to deform without cracking. Any strain hardening that occurs is immediately relieved by recrystallization. One common hot working process is hot rolling. And in hot rolling, the metal is passed through rollers to reduce its thickness or create bars of specific shapes and dimensions. This is typically how structural shapes like I-beams or round bars are produced. Extrusion is another hot working method. Here, very high pressure is applied to force the heated metal through a shaped orifice, kind of like pushing toothpaste through a tube. The result is a long piece with a constant cross-sectional profile. This is often used for making things like rods, tubes, or even complex aluminum profiles. And finally, forging is essentially modern-day blacksmithing. It involves shaping metal using hammers, presses, or other specialized forging machines. And it produces very strong parts because it aligns the grain structure of the metal, which improves mechanical properties. Now, how about cold working processes? During cold working processes, the metal is formed at room temperature. One cold working process is spinning, which is used for sheet metal. So in spinning, a flat metal disc is rotated at a high speed and pressed against a shaped form to create a circular symmetrical part. This is commonly seen in parts like metal bowls or satellite dishes. Stamping is another widely used cold working process. It involves punch press operations like blanking, coining, forming, and shallow drawing. These are often used in high volume production for making parts from sheet metal quickly and efficiently. Now, cold rolling is used to produce wide flats and thin sheets with improved surface finish and dimensional accuracy compared to hot rolled products. Cold drawing starts with hot rolled bars that are first cleaned and then pulled through a die to reduce their size, typically by a 16th or a 32nd of an inch per pass. And then to reach the final dimension, the bar often needs to be drawn multiple times through progressively smaller dies. This increases the production cost, but cold drawing and other cold worked parts have a bright new finish, are more accurate, and require less machining. So that trade-off is worthwhile for many applications. Okay, and I'm boxing this last statement because if there's nothing else that you remember from this comparison between hot worked and cold worked parts, I want it to be this. Remember that the cold worked parts will, as compared to hot worked parts, have a nicer finish, be more accurate, and require less machining, although they will typically have higher production costs. So now let's think through some examples. And for each of the following applications, I want you to pause the video and think about whether hot rolled steel or cold drawn steel would be more appropriate. Okay, got your answers? For A, for railroad tracks, if you guessed hot rolled steel, you are correct. And the reason for that is that mostly we need bulk production of railroad tracks, and we don't particularly care if it has a bright new finish, and it doesn't need to be particularly accurate. It does need to be somewhat accurate, but not as accurate as, say, machine keys, where we definitely prefer cold drawn steel. And then how about metal furniture? That one is also cold drawn steel, largely because we want that nice bright new finish for furniture. And lastly, structural I-beams are going to be hot rolled steel. Again, we want bulk production, doesn't need to be as precise or accurate as a machine key, and we don't care about having a bright new finish. All right, now after your part has been either hot rolled or cold drawn and it's formed, the last step is an optional heat treatment. So let's talk about how that works. Heat treatment in general refers to the process where we carefully control time and temperature to change the properties of a metal, most commonly steel. Now, steels are heat treated for multiple reasons. One of those reasons is to relieve residual stresses. Residual stresses are internal stresses that remain in a part even after all external forces or temperature gradients are gone. And these residual stresses can result from welding, machining, or cold working. If not addressed and relieved through a heat treatment process, they can lead to warping, cracking, or even premature failure over time. But keep in mind that residual stresses can be beneficial. So for example, when we roll the threads on threaded fasteners that leaves us with compressive residual stresses that are beneficial to the performance of the fastener most times. Another key reason to heat treat steel is to modify its material properties. Depending on the process, we can increase hardness and strength or improve ductility and toughness. So, for example, we might harden a surface for wear resistance while keeping the interior tough and ductile to be able to absorb shock or impact. So, in short, heat treatment is a powerful tool that allows us to tailor a material's behavior to suit specific engineering needs, whether that's making something stronger, tougher, or more stable. Let's talk about a few different types of heat treatments. So first up is annealing. Now, annealing is used to soften a material. It increases ductility, relieves residual stresses, and refines the grain structure for a better overall performance. During annealing, the material is heated to about 100 degrees Fahrenheit above its critical temperature, and it's held at this temperature until the carbon dissolves and diffuses through the material. After that, the material is allowed to cool slowly, usually just right in the furnace where it was heated. This slow cooling is key. It helps develop a more uniform and refined grain structure, which improves the metal's properties. So annealing is commonly used to prepare metals for cold working because it makes them easier to shape without cracking. It also enhances machinability and can improve properties like electrical conductivity for certain alloys. So in short, annealing helps reset the material structure to make it more workable and reliable for the next stage of manufacturing. Now, next up we have normalizing, which is a specific type of annealing, but with a few key differences. In normalizing, the material is heated to a slightly higher temperature, and then after holding it at that temperature, it's allowed to cool more quickly, usually in air instead of inside the furnace where it was heated. And because of this faster cooling, the resulting steel is harder and stronger than fully annealed steel, though it's generally less ductile. So normalizing is often used when we want a balance between strength and toughness with a refined and uniform grain structure. Next up, we have quenching. Quenching is a heat treatment process that involves a controlled, rapid cooling of the metal, usually simply by immersing it in water, oil, or some other cooling medium. After quenching, the material will become very hard, but this hardness comes with a trade-off. It also becomes brittle. Because of the fast cooling, the metal doesn't have time to undergo full annealing. So instead, the microstructure will shift from the softer phases like pearlite to harder phases like martensite and bainite. This makes quenching ideal for applications where we want high hardness and strength, but it often requires further treatment after quenching to reduce the brittleness. Now, one way to do that is through a process called tempering. So tempering is a heat treatment process that follows quenching. In tempering, the steel is reheated to a temperature below its critical temperature and then cooled in still air. This controlled reheating allows us to adjust the steel's ductility, hardness, and toughness to achieve a balance of those mechanical properties. One interesting aspect of tempering is the appearance of different temper colors on the steel's surface, and these colors, which range from a light straw color to a dark blue color, provide a visual cue to the final properties of the steel. So, for example, very hard tools are often tempered to the light to dark straw color range, indicating high hardness with some toughness. In contrast, springs are typically tempered to a blue color, which corresponds to higher ductility and toughness. So, tempering essentially relieves some of the brittleness introduced by quenching, making the steel more practical for real-world applications. Now, the last heat treatment process we're going to talk about is case hardening, which is a heat treatment process designed to increase the hardness on the outer surface of a metal part while maintaining ductility and toughness in the core. This is typically achieved by adding carbon to the outer surface through exposure to a high carbon environment. This can be solid, liquid, or gas at an elevated temperature, and this process is often called carburizing. Alternatively, case hardening can be accomplished by heat treating only the outer surface without changing the core. So some common methods to achieve that include induction hardening and flame hardening, which rapidly heat the surface and then cool it quickly so that we harden just the exterior. And I'm going to throw up a picture of a flame hardened sprocket, and you'll see some discoloration around the teeth that delineates the area that was rapidly heated and then quenched to form these case hardened teeth. The result combines wear resistance and a hard surface with a tough, shock-absorbing core. So this is ideal for components like sprockets, gears, cams, and shafts. So just to wrap this all up, I'm going to give you an example question that I might include on an exam. And the question asks, I have a steel shaft that experiences high torque starts and stops. During running, the shaft also experiences moderate shocks. So which is the best choice for heat treating the shaft? Okay, and our given options are A, annealing, B, quenching, C, tempering, or D, case hardening. So pause the video if you need to, try to think about this, go back, look at our notes from earlier in the video, and then let's talk about the answer. So, if it were annealing, if we were to anneal this shaft, we would just soften the steel, which is not desirable in this case because the shaft needs to be able to handle high torque and shocks. If we were to quench it, quenching alone would just make the steel brittle. So this would increase the risk of fracture, particularly under the shock loading. If we were to case harden, that would harden only the surface while leaving the core softer. This is typically used for components like gears that need that hard, wear-resistant surface, but it's less ideal for shafts subjected to high torque throughout the cross-section. So, tempering strikes the right balance between hardness and toughness. So, if you got that right, great job. I hope that this video was helpful in understanding different types of materials processing, particularly for steels. And in the next video, we will talk about some mechanical properties of materials like steel in preparation for getting into a meatier topic, which is failure prevention. So I hope you're looking forward to it, and thank you for watching. Hope to see you in the next one.